All right, welcome back to part two of building this complete ADC to DAC system. So in part one, we basically set up using CubeMX this system with an ADC that's being read by DMA thrown into a ADC buffer from which we said we would process the data and then put it in a DAC buffer. And we were doing a upper and a lower buffer kind of configuration. Okay, so that's where we were at. We had generated the code on CubeMX side of things. So here's my code that CubeMX generated, and I built it. And the last time I was exploring some functions. So let's go and fully try to understand how these functions might be explored in the CubeMX. So here we are. So by this is the default view of the files. Uh, Again, the peripherals ADC, DAC, timer, and the DMA are listed. Now, if I go to the function side of things, and in the interrupt, I have the DMA1 and the DMA2 interrupt handler. So let's take a look at this because DMA2 is currently tied to the A to D conversion peripheral to memory. Peripheral to memory. So here is my void DMA2 stream IRQ handler. So what happens when uh, the DMA gets interrupted? And when does the DMA get interrupted? Basically, the DMA is going to get interrupted two times. One is going to raise a flag called the half transfer complete flag. So that means half of the ADC buffer that has been designated has been filled. The next time it's going to interrupt is when the full buffer is complete. So you can know when you have half the data ready and full data ready. That's when you get different flags interrupting the DMA. So that interrupt will bring me to the DMA stream IRQ handler, which calls the HAL DMA IRQ handler with the ADC1. So let's right click on here, go to the definition of that. All right, so now we're at here, and if we browse through this, this handles the DMA interrupt request. The DMA handle is coming from the ADC connected DMA, and there is a couple of flags that are checked. If there's an error, it takes you to the error handler routine. But what we are really interested first is in the half transfer complete interrupt management. So this case, we got to this position right here when the half of the DMA is the half of the ADC buffer is full. The DMA raised its flag. We got here, and that is going to take us to the call half complete callback handler. Now that handler is tied to the ADC, so let's go open up the HAL ADC.c, and I see the first couple of ones. The first one is called the HAL DMA conversion complete callback, and the other one is called ADC DMA half conversion complete function. So let's double click inside this. HAL ADC DMA, so let's double click and say, oh, here you go. So ADC DMA conversion complete, pointer to a DMA handle structure that contains the configuration information for the specified DMA model, is the parameter that's getting passed to it, and this is a function that gets called when the DMA is half complete, or the buffer is half complete. So what does it do? It basically calls the HAL ADC convert half callback function. So if I go to that function now, I see that there's a weak function called HAL ADC convert half complete callback. Now, if you remember the ADC interrupt that we did in prior video, we got an ADC interrupt, and the ADC interrupt handler had a weak function inside it called a HAL ADC conversion complete callback function. So that was a weak function that we overrode in main. In this case, when the half of the ADC buffer is full and the DMA half conversion complete callback is done, we will be executing this particular function. So we need to create a stronger version of this particular function in main. So let me copy that and bring it to main under user code begin 0. So we'll have to eventually write and complete this. Similarly, when the HAL DMA buffer is full, uh, so HAL DMA buffer is full, we will have to again go and write what happens there. ADC DMA conversion complete callback. Uh, we'll look at this, and eventually it calls the HAL ADC conversion callback routine, which is a weak function right here. And we'll have to bring this into main and create a stronger version of that particular function. So let me get rid of the unused version of that function. So we will be editing these two functions to make sure we have the necessary thing that needs to be done when the DMA buffer the ADC buffer is half full or complete full. Okay, so that's what we'll do next. Now let's go back to the function. So the one of the first thing we want to do. So in main, HAL has been initialized, the clocks have been initialized, the GPIO. Since the ADC and the DAC pins have access to the GPIO, those pins have been configured for those particular settings. DMA has been initialized to do the memory to peripheral, peripheral to memory, auto increment, all this kind of stuff. You can dig through what happens in these initializations by again going and right clicking and seeing what's happening. DMA1 and DMA2 clocks are being enabled. The priority of the interrupt is being set and all that kind of stuff. So you can dig through yourself. So we have ADC1, DAC being initialized, the timer 6 is being initialized. So one of the things we need to do is start the time base for the DMA channel. So HAL, oops, that was an autocomplete. HAL time HAL time base uh, init, and we are going to do STM. So that is the handler for timer 6. So we'll initialize the timing base. That's what we'll do there. So HAL time base. Oh, not initialize. Sorry. Start. We need to start the timer 6. That's what we'll do. Okay. Next, what we'll do is we want to start the ADC DMA. So HAL. I don't remember the function, so let's go take a look here. Under HAL ADC. Okay, we'll find HAL ADC start. When we want to start, but we want to start with the DMA. So HAL ADC smart start uh, with a DMA. So HAL ADC start with a DMA. And what it's expecting for parameters, the first parameter is the pointer to ADC1. The second it's expecting is Uint32 pointer to the data. So we'll create a buffer to store our data. For now, let me just Uint32 underscore T and a star, and let's call this ADC val. So I haven't created this memory array. We'll do that let's go do that first before I actually forget. So so we'll come back to this. There's an error right now because I haven't completed, but I'll come back to that in just a second. So here, let's go to private variables and let's start declaring our variables, and we'll call it create ADC and DAC buffer. Okay. And before we do that, actually, let's call begin private variables. So here you go. First, let's define what our size should be. So define, I'll call it data size of 128, and I'll define the full buffer size to be 256. Okay, what have I just defined? I basically defined this upper and the lower halves to be 128 each, so that's what I call the data size. That's the data size we'll be processing, and I've called the full buffer size twice that value. 128 times 2 is 256. Okay, that's what I've done. Uh, so I'll write down some comments here. So this is the full ADC DAC buffer size, and this is the number of samples user accesses uh, per data block. Okay. All right. Next thing we want to do. All right. So we've done that. We will create a ADC and DAC buffer. So let's create a ADC and DAC buffer. So we'll call them uint32 underscore t ADC underscore val full buffer size. And I'll do the same thing, but this time it'll be the DAC val. So I've now initialized this buffer and that buffer right there. So that's what I've done. Okay. Uh, okay. That create a DAC buffer size, data block sizes for streamed ADC DAC variables. So we should be good for now. So let's go down here. So I was in the process of writing the HAL ADC start with the DMA. We called my function ADC val. Next thing it wants to know is basically uint32 underscore t length. So what is the total size of this buffer that the DMA should be filling? Okay, so we call that the full buffer size. I believe full buffer size. Full buffer size. All right, so that should be good. So we've initialized or started the ADC based DMA. Now let's do the same thing for the DAC. Start DMA HD it's DAC. Now what does it expect? It expects a channel number. So the channel numbers are called DAC underscore channel underscore 1. So we're using DAC channel 1. It is expecting the next parameter they're expecting is let's go see HAL DAC under start with DMA. So the next after channel it's expecting a pointer to the data. So in this case let's this, but it'll be called DAC val. The next thing is the length. DAC underscore val is the name of the array. The length is full buffer size. And the final thing is called the alignment. So let's find out what that really means. So the alignment, HAL start DMA. So here, alignment specifies the data alignment for the DAC channel. We're using a 12-bit right aligned data. So DAC aligned 12-bit left and DAC aligned 12-bit right. So we want the 12-bit right. So that. And that should be our end of the initialization. So the timer is now starting and running. The ADC buffer is going to start. The ADC is going to start the DMA transfer. The DAC is going to grab from memory and throw it out to the DMA. DMA is going to throw data from the DAC buffer into the DAC channel. Okay, so now, okay, so that's all set. All right, so what do we really want to do next? What we want to do next is figure out what should happen when we get to half complete. So let's say we got to a point called half complete. All right, let's see, half complete. This pointer, okay, if this is half complete, we want the pointer for the processing data. So this is all filled and I want to start processing this while the DAC starts to fill this. So we're in this kind of setting. We want this pointer to point to the top of this array. We want the data to be written in the bottom half because we're assuming that the top half is being emptied right now. So we want a buffer pointer. So let's create two pointers. One we'll call input pointer or inbuff pointer, let's say, and the other one we'll call the out buff pointer. So let me go and at the very beginning, right where we had the declarations done, let's call it pointers to the half buffer, which should be processed. Okay, static volatile uint STM32 underscore T star in buff PTR. And that's the input pointer. That's called in buff pointer, and I'll create another one, same thing, and I'll call it the out buffer pointer. Okay. Uh, Now that the pointers are done, this is what I want to do. ADC. All right. So oh, let me minimize this a little bit, and with my picture, this is what I would like to do. When I am half complete, so when I'm half complete, my half complete, uh, I want to be processed. So the top part right here, this is complete. So I want my processing function to be grabbing data starting at the very top. So that's index 0 of the ADC buffer. So what I want to do is I want to create a pointer called, we've created the pointer. Uh, so this is why first half of the ADC buffer is now full. Uh, in buff pointer equals ADC underscore val. Let's call it conversion complete callbacks. First half of the ADC buffer is now full, so the pointer is pointing to ADC val 0. The out buff pointer, out buff pointer is going to point to the DAC val, and that is going to be at the halfway point, right? And in this case, we'll do the exact opposite. So let me copy this, paste it here, and change this to data size and this to 0. So essentially what we're saying is, in this case, the input pointer, when the input pointer for processing is pointing to the top, the output pointer is pointing to the bottom. So this can be emptied out to the DMA. So, so this kind of case, right? So this is what we're talking about. Okay. All right. So I think we have it all set. So let me save this and see if I can build my code. Uh, 0 errors. Set but output pointer is set but never used. Okay, that makes sense. So we basically pointed this. We need to create this particular function. So let me call my function, I don't know, process DSP. So I'll call it void process DSP, uh, and we'll do something useful inside here. And let me put a comment here. So placeholder for now. For a DSP function block. And for that function, what we'll do is for autocomplete for oh my god for int n equals 0, n less than the data size n plus plus. And what I want to basically do is out buff pointer n equals, let's just make them the same. We'll just basically pass on the value. So we have a very complicated DSP function right here. So this is basically a placeholder for any useful DSP function we might do later on. Data size, what happened here? Use of undeclared, data size. In buff pointer is what I call it, not input. So out buff pointer is equal to in buff pointer. So where will we do this? We'll basically call this function inside the while one loop. So right here. All right. So initialize the time base. We started the DMA. When the ADC DMA is done, halfway done, it'll basically include a pointer, which will then be used to process the data. So here we have the output buff equals input buffer pointer. So we're basically saying that the data is output coming out is should be the same as the data going in. So if I build this, all right, I'm going to set up my waveform generator. So I have a waveform generator that I've created. I'm basically going to, so only channel one is connected. So channel one is currently connected to ADC one. So I'm going to enable this right here. And on the scope, I let me let's go to the debug mode first. Download to Flash. Okay, so I am basically going to hit run on this side, and we should see the ADC value changing right here on the debugger. At the same time, let's see, let me go add the DAC val. Add DAC val to, let's say, watts 2, and if I look at that value is also changing with time. So let's see what that change really looks like. So on the oscope, I'm going to hit run. I'm going to bring up the oscilloscope. Uh, This blue channel right here is the input buffer data. So that's connected. I have it probing the data going into the ADC1. The yellow is the data coming out of the DAC. So let me just do a single channel. So you see the data input, that's the data output. So if I look at here, right here, I have a 1 millisecond lag for the data output to the data input kind of deal. Okay, so I have data coming out, data going in, and they look exactly the same. So in code, let's go back, and we had a very simple function. So let's make it just a little bit, tad bit complicated. Let's divide this value input buffer pointer by 2. So another one way to call that is just shift by 1. And now what we should find is that the output value should be exactly half of the input buffer. So if I set up the debugger again and set it to run, okay, and set it to run. And if I look at the oscilloscope again, so let me run the oscilloscope. And now let me do a single sweep so that I can stop. Overlay these two guys so the ground lines line up. I see that the output value is half of my input value as I had done in the code. So basically, process DSP is the function I would modify for other DSP functionalities later on. We can change the size of the buffer, how many do you want to be bringing? 32 points, 64 points, 100 points? That's completely up to you and the algorithm that you'll be writing for DSP processing later on. Okay, so to do a quick recap, we created this particular system right here, employing DMA to grab data from ADC, employing DMA to grab data out of the buffer into the DAC. And we created a very simple processing data function, which can be replaced later on with a more complicated DSP routine like FIR filters or any kind of processing that you want to do on a block of data or a sample by sample basis for the data. Okay, so that's all for this particular video.